So to take these notes, you'll either need to print off the PDF that's in your Schoology folder, or if you stopped by my room and picked it up, or we're in sixth hour, I gave it to you, or you can just take it in notebook paper too. So when you're done, there'll be a quiz on Schoology. There'll be 10 questions directly off of these notes. So make sure you write everything down and use the notes while you take the quiz. It will time out if you try to take it while you're taking the notes. I have a time set on the quiz. So the method is watch the notes, write everything down that I write, and then go take the Schoology quiz by midnight on Sunday. So we're moving into the second to the last topic, exponential growth, and then next year we'll expand this into something called logistics growth. But as you know, with exponential growth curves, they start off quite slow and then they shoot up exponentially. There's nothing that limits their growth. It's just the more you have, the more it keeps on growing. Usually, though, what's more common in the real world is things start to grow very fast, but then there's some limiting factor that causes them to taper off. We call that like a carrying capacity. It could be food supply, it could be just space or something, but usually something causes stuff to taper off, and you get this blue thing, which is called a logistics curve. And those are really interesting with real world examples. We're not going to do those this year, though. We're going to focus on exponential. So things are going to start off growing, and they're just going to grow faster and faster. So it says the rate of change of some quantity y, and that would be written as dy dt, its rate of change over time, is directly proportional to y. I want you to put that in the box. That's your green light for exponential growth. When they say something's directly proportional to the amount present. Now, if it wasn't dy dt. It can be anything changing over time. It could be bacteria growing over time. It could be a disease that's spreading over time. It could be your money growing over time when you invest it. Those are all rates of change. And if they say that they're directly proportional to y, what that means is they're directly proportional to the amount present. Now, in a real world context, it just means that the more bacteria there is, the faster it's going to grow. It's proportional to the amount there at any given time. So the bigger B is, the more you're going to have. Same here. This would be directly proportional to the amount of people who have the disease. The more who have it, the faster it's going to spread. Same with your money. The more money you have, the faster it's going to grow. So, the key phrase in this is directly proportional to. That means multiplied by some constant k, and we call this k the constant of proportionality. So we're going to have two constants in these scenarios, an integration constant, which we're going to call c like we always have, and a constant of proportionality that we call k. And I believe that's what they call it in algebra 2. I think when they do variation, I think they call the constant of variation a k. But I'm not sure because I don't teach that course. But usually k is traditionally known as a constant, but it's known as a constant of proportionality, not an integration constant. All right, so what we're going to do is take this differential equation, this rate of change, and we're going to manipulate it using our process of separation of variables so that we can get a formula for the amount there. Now, in a real world context, what that means is, okay, so I know the rate that bacteria is growing because I took a throat swab and I put it in a dish and it's starting to grow, and I'm a biologist or somebody working in the medical field or in a lab, and I wait for it to grow, and it's going to grow proportional to the amount present. The more there is, the faster it's going to grow. If it grows at certain rates, it means you probably have a disease like strep throat. When you go get your throat swab, they make you wait for half an hour because they're waiting for this to grow fast enough. And if it doesn't, it means you don't have strep. So what we're going to try to do is figure out, well, what is a formula for the amount of bacteria there at any given time? That's what I want to know. And we're going to solve it completely once, and then we're going to memorize it, which I rarely say. But when you solve a direct proportion, meaning the rate of change over time is directly proportional to the amount present. To solve that for y, the same algorithm gets applied and the same thing happens. To solve this for y, we pretend we're in last chapter. We get all our y terms on one side. So I would do 1 over y dy is equal to just K. And remember, in this case, K is a constant. It's not an integration constant, though. Remember, it's a constant of proportionality, we call it. So 1 over y dy is equal to K dt. And I'll separate. It's not a hard separation. It's not a hard integration. This is natural log. Technically absolute value, but for the real world problems, things don't go negative. They grow or they shrink, but if they shrink to 0. They don't go negative. So you can completely trash your abs-vabs on that. This would be KT plus. Again, now we have a new constant. So these problems have two constants in them, a constant of proportionality and a constant of integration. To solve for y, we do what we've always done. We exponentiate. So nothing new going on here, but this will be the only time we do this in this section. The same thing will happen every time, regardless of whether this was bacteria growing and it was directly proportional to the amount present. This process would hold. I just have B's instead of Y's. Or if it's a rumor spreading and it was directly proportional to the number of kids who knew the rumor, this would be the exact same process, just my Y's would become R's. So we'll do the process one time. What would always happen is we'd get a Y here, or a B, or an R, and it would equal. Remember what we do in this scenario, we disengage that constant from the exponent, and we call it some other constant. Here's the problem. We can't call it K anymore because K is the constant of proportionality. So usually what we'll do initially is we just call it another C. So when I do this, I get C e to the KT. A lot of people will call this the sect model because it looks like it spells sect like this. So you might want to memorize C e to the KT. However, the C is always going to be the same thing in this scenario, so I would advise, and this is going to be one of the quiz questions, I would advise that you remove it. Think of sect like C e to the KT, but what it's always going to end up being is the amount present at time 0. So whatever that is, again, the bacteria example, if it was dB dt and it equaled Kb, I would have solved that whole thing and I would have had B equals C e to the KT. But this is the amount of bacteria present initially, because when you put in a 0, this goes to 1. So whatever they say was there at the start, so I want you to point at that and write start, or at time 0, comma, and we call that y sub 0 or y of 0. So you're going to remember the sect model, but I highly suggest you replace the C with a subscript of 0. So here's the kicker to it. Before I go do an example, you need to be 100% confident that when it says the rate of change of something over time, and let's say that stands for money, is directly proportional, is directly proportional to the amount present at any given time. This is what we call the differential equation. So if you're asked for the differential equation, that's what you write. If they ask for the solution, you say the solution is the amount present, y is equal to, and you're going to think sect, C e to the KT. However, this right here is always the starting amount. So I would suggest you say the amount at time 0, e to the KT. Now this looks an awful lot like a model you would have had in a previous math class. If I were to replace these variables with this is the amount of money you have after a given amount of time, this is how much money you put in the bank, which we call the principal, e to the KT, it almost looks like PERT. Well, that's because the R in that scenario is the constant of proportionality. So that kind of ties in with something you should already know. Now that was a lot of words, so we're going to go do an example. I'm going to take that bacteria example and run it through. So bacteria in a lab, let's call that B. If it was people in a pool, call it P. If it's money in a bank, call it M. Make sure your variables represent what you're finding. Don't call them Y's and T's. Bacteria in a lab culture grows in such a way that the instantaneous rate of change, that would be dB dt. so that's a derivative, of bacteria is directly proportional. That's that key word. That means you're going to have a constant of proportionality called K, and it's directly proportional to the amount of bacteria present, which is B. So when it says write a differential equation, that just is to take that and say the rate that the bacteria is changing over time is directly proportional to the amount present. It will always look like that. Whatever this is here goes here with a constant of proportionality in front of it. Then it says to solve it. We're not going to solve it. I just told you on the previous page that the same thing happens all the time. You get y is equal to sect. But in this particular problem, we're solving for b. So we'd say the amount of bacteria present is, and right here is always the starting amount. So I would put bacteria sub 0 for the amount at time 0, e to the kt. So although it's the sect model, I found after teaching this for 5 years, go ahead and think sect, but replace the C with the starting amount and replace the Y with whatever you're finding. All right, so no need. If you were to separate, integrate, and do that whole process on here, this is what you would get. So I've got two things with vocabulary. I've got my differential equation, check. And I've got my solved differential equation, which I'm going to put in a box right here. All right, how much time am I at? Super. All right, so it says suppose there are initially 5 million bacteria. Initially. That means at time 0, there's 5 million. So they're giving you a point. By the way, because you have two unknowns, B sub 0 and Carl, or generically C and K. You have two unknowns, they must give you 2 points. How many points must they give you? 2. They have to give you the start. You can't chart growth if you're not charting what it starts at. So whatever it starts, they will tell you. This they told me 5 million before I started charting the growth of this bacteria. After 3 hours, it had grown to 7 million. They just gave me another point. And again, if I were to label these with function notation, I could say that this is T, this is bacteria after time T, this is T, this is bacteria, it's kind of like X, f of X, but we're expanding this to apply it to the real world. It says, write the particular equation that expresses the millions of bacteria as a function of hours. So I want an equation for how much bacteria will there be at any given time. So I start it like this. I actually have that right over here. I already solved it. So I've got my bacteria is equal to B sub 0 e to the kt. I need to use my 2 points to supply this and to supply that. E is always in there, T is the independent variable, and B is the output. This first one, B sub 0, was given to me. They told me at time 0, I mean, you can go plug a 0 in for T, but that's a 1, and you're going to get 5 for your constant out front. All right, so that's what I know. Really what the kicker always is what is K? You always need to find K. And that's where the second point comes in. You know that when T was a 3, the bacteria had grown to 7. So we're going to say the bacteria is 7 million, started at 5, and grew for 3 hours. So I can solve this for K by dividing by 5. So I'd say 7/5 is equal to the E to the 3K. I like to put the number out front. I'll take the natural log of each side to get rid of the E. And so my K is going to equal the natural log of 7/5 over 3. And right now what I do is go to your calculator. And if you could do the natural log of 7 divided by 5, make sure it's locked and loaded in parentheses. Divide it by 3, and I'm going to round it on my paper, but what I would suggest you do is store it. You're going to get a 0.112157, 0.112157, and I don't want to type that through the rest of the problem. So right now on your calculator, at the bottom left above your on button is that store. Hit store and put it in K. So hit store alpha K. Again, you don't have to, but that's a very a recommendation for you. Don't round it. Don't keep writing it over and over again. We're going to use it for 2 more questions. We'll just store it in K and bring it up when we need it. And that way I don't have to write it anymore. So, next question says, what will the bacteria population be? That's a question about B. All right? I want to figure out what is B. 1 full day. And they're telling me my time. Now this is in hours, so I'm going to have to use 24 hours for 1 full day. I have a model for my bacteria growth. Let's go back to what it is. My bacteria model is the bacteria at any time present will be equal to sect, the starting amount, which was 5, e to the kt. And I've already stored that. So that's stored in my calculator. So really with this question, I just need to take and do 5. Then I'll hit e to the, my t is going to be 24, and I'll just hit alpha k. I already have a number stored in there. So go to your calculators and do 5e to the 24 times, and then just hit alpha k, and you don't have to retype it. And I get 73.790 if I were to round right, 73.790. Keep in mind that this problem was giving me the start in millions, so my answer would be million bacteria. Well, maybe there's some health hazard if it's over 75 million. So maybe I'm safe for now, but I'm getting close. This is actually a very applicable skill for growth. But again, like I told you at the very beginning, most things do not grow exponentially. In Algebra 2, you learn about linear growth. Almost nothing grows linearly. That's kind of like if you get paid $200 a week and you just put it under your bed and you just keep adding 200 and 200 and the same amount, or that constant rate of change. Most things when they go have a varying rate of change, but again, most things start off quickly and something makes them taper off. And this is a concern for us later on. It's pretty cool. All right, so the next question says when. This is a question about t. I'm going to have to solve this for t when b is a billion. All right, I'm going to write my model down though. B is equal to c e to the kt. And you might say you said c. I did, but remember we think sect, but we put the starting amount for the situation. And again, we said ours was starting at 5 million. I'm in search of the time that it'll take for this to grow to a billion. I can't put a 1 there though. This problem's all in millions. So I have to think about a billion and how many millions it is. And that's 1,000. So I'd have to grow to 1,000 million when I started at 5 million. E to the k, which I have stored, t. That's what I need to solve for t. And this just requires some algebra and some natural log skills. So dividing both sides by 5 gives me 200 is e to the stored kt. Again, I'm not writing 0.11, whatever k was. I'm not going to write it. That's what it provides ease when you store. Now I'll natural log both sides. Natural logging e to the kt is just going to give me kt. So for my time that it'll take to grow to 1,000 million, aka a billion, is the natural log of 200 over k, which I have stored. So you're going to go back to your calculator, you're going to natural log of 200, and make sure you're using your calculator while you're doing these. Divided by, and you're going to bring up your alpha k, whatever it was, whatever, I don't even remember, and we'll round to 3 decimal places. It'll be the time that it takes, about 47.24 hours to grow. Maybe that's how long it takes until I have some sort of an epidemic that can break out. Maybe I need to get that growth to taper off somehow and make it, there's a huge implication for all of this. Next up, see how far I can get. During an epidemic, the number of people infected at any time increases at a rate proportional to. There's your exponential growth model Q. Number of people would be P. Rate is a derivative. It's proportional to the number of people infected. That means this in calculus. The rate, and let's do just people, over time is directly proportional to the number of people infected at that time. My guess is the more that are infected, the faster the epidemic will grow. It's going to give me exponential growth. We are not going to separate, integrate, and all that on here because I told you the model always yields y equals sect. So P equals sect. But our C is always the amount present at time 0. So it gives you a nice model for remembering it. The question says if 1,000 people are infected when it was first discovered, there's my 0.01,000, there's my P sub 0, it's going to go right into my model. Done. They need to give me a second point so that I can figure out my constant of proportionality. And they hand it right in my lap. They say 1,200 are infected 7 days later. So I'll go to my model and say 1,200 are affected 7 days later. So again, I'm going to repeat the process. We write our differential equation or our DEQ first. Then we write the sect model, replacing the C that's in the model with the starting amount. Then we put in our initial point, and then we solve for K. So when I solve this for K, I'd get 1,200 over 1,000. I'm going to knock off a couple zeros here. I'd get 12 over 10. 6/5 on the left would equal e to the 7K. Solving that for K, I'd get ln 6/5 is equal to ln e to the 7K. ln undoes e. So to get K, I will do natural log of 6/5 divided by 7. Now these answers are so far apart, except for these two right here, that you could probably go round that on your calculator and not store it. And we're not going to use it again either. So go do natural log 6/5 divided by 7. And what do we get? We get about 0.026. So K is about 0.026. Let's go point at that, 0.026. Question was, how many people, looking for P, infected 12 days later gave me T? So I go to my calculator and I say there were 1,000. Enter it on your calculator. E to the 0.026 times 12. They gave me the starting amount, 1,000. I found the constant of proportionality, and I'm plugging it all in. And if you do that correctly on your calculator, it should yield C. So give that a whirl. And again, these are actual AP questions I've screenshot off of this topic. Next one says population of Y grows according to the equation. You need to recognize, hey, that's that exponential growth model with a constant of proportionality. It says K is a constant, T is in years. Population doubles. Now I told you they have to give you 2 points. They don't if they tell you things are doubling, tripling, or have a half-life. So off to the side over here, I want you to write this. Doubles. What does that mean if they tell you something's doubling? It means it was at y sub 0 for the start and it grew to twice that. If they tell you something was tripling, it means it started at some amount and it grew to 3 times that. If it's some drug or radioactive material that has a half-life, it means it started at some amount and got cut in half. So they'll tell you how long that takes, but when you are setting up ones where it says doubles, triples, half-life, this is what you're thinking, and then you can take a shortcut. Again, the solution to this is y equals c e to the kt, but c is the starting amount, so I'll go like this. They didn't tell me what it started at. I could actually put in a fake one. I could put in a 50 and have it double to 100, or I could put in a 60 and have it double to 120. But regardless of what happens, when it doubles, it's going to go to this. And so I can cancel those off. So when it says doubling or tripling, you get a nice simple equation like this. Had it said tripled, that would have been a 3. Had it said half-life, that would have been a half. So it said it took 10 years to do that. So this is a 10. My goal was to figure out the value of K. Well, natural log both sides. I'd get ln2 is equal to 10K. ln e to the stuff is the stuff. And all I do is divide by 10. Now there's a shortcut for these that we'll focus on more in Calc 2. So I really want you running through the process. I don't know what that is on the calculator, but I'm assuming it's this since I have it starred. But so the shortcut is this. If you know the growth factor, it's actually the natural log of the growth factor over the time it took to do that. So your constant of proportionality, if it takes 4 hours for a drug to reach its half-life, you would say ln of a half divided by 4 is what would pop out. But you don't really need to know that. By the way, half-life is used a lot in the medical field. I remember, we're not going to do this one right now. That's not on this topic. But when I had a surgery a few years ago, one of the common questions they ask you before a surgery is, have you taken any medication? And at the time I had been going through chemotherapy and I was on a specific drug, and I said, well, yes, I've taken whatever. And they said, well, that's no problem because that has a half-life of 5 hours. So what that means is it was half out of my system 5 hours after I had taken it, and I had taken it at 6 at night. So this was a surgery the very next morning, which means there wasn't enough of it in my system to impede or affect the surgery. So in the medical field, tons of half-life. Also for radioactive waste and stuff, that you're going to do a problem that does the Chernobyl thing, and you're going to figure out how long it'll take. If you are familiar, people still can't go in that area because the radioactivity is too high, but we're going to work with that one too. Next up, easy question if you understand the model. It says dy dt equals ky, and k is a non-zero constant. What could y be? This is your exponential growth model. We can jump right to y without separating, integrating. If we remember, y equals sect. There's only one of these in that model. No, that's got an xy, and this has got some plus on it. I don't know what's going on with this. None of these are even exponential. This is the only one in the sect model, and that would have had a c of 2. And it's done. So I think I'm going to get one more, the last one in here since I'm going. So this next one will be the last one I do for your notes. When you're done watching it, go take the quiz right away, and you should get 10 out of 10. You accidentally inhale some poisonous fumes, silly Sally. 20 hours later, you're still feeling a little woozy, so you go to the doctor. They draw your blood, and they find a poison concentration of 0.0032. They just handed you a point. At the time you went to the doctor, which we're going to call time 0, you might say, well, you went 20 hours later. Yeah, but that wasn't when the initial quantity was measured. So we're going to say time 0, the concentration in my system was 0.372 milligrams per milliliter. And he says, you're going to have to come back 8 hours later, and we're going to have to see how that's left your system. And on a second visit, he measures the concentration to be 0.00219, and that was 8 hours later. So I was handed 2 points, and you have to have that with these models of growth. You need the start and what's happening later, and then we can answer all sorts of questions. In this point model, this would be C, and this would be my concentration after time t. So we've got t, concentration after time t. Next up, it says let T be the numbers of hours since your first doctor visit. Copy that. Let C be the concentration. And this is where some people who memorize things and not understanding the concepts goof up, because C is now standing for something entirely different than what you're used to. C is the name of the function, and it stands for the poison concentration. So got to be a little careful how we use our variables. The rate of change of C, oh, there's my derivative, directly proportional to, there's my exponential growth trigger, to the current value of C. Write a DEQ, differential equation. The rate of change of concentration in my blood over time is directly proportional to the amount in my blood at that time. Now, because over time the concentration in my blood is obviously going down, you can probably use intuition to know that your K is going to end up being negative in this scenario. This is going to be exponential decay. So we have growth and decay models, and they're controlled by the constant of proportionality being positive or negative. All right, here we go. It says solve it. Don't need to reinvent the wheel. Y equals sect, but you have to understand what those stand for. This is what I'm solving for when in this case is the concentration of poison in my blood, is equal to C sub 0, okay, the starting amount, e to the k t. There it is. I didn't solve it subject to the initial conditions. What that means is you need to go fill in your missing constants. We have this one, which is handed to us, and we have constant of proportionality, which we need to find. So when I put in 0 for t, they told me it started at 0.372 e to the kt. So I replaced the start amount right off the bat. Then I use my charted growth, in this case my charted decline or negative growth. I know that it shrunk to 0.00219 after 8 hours. So, sorry, that's got to sound awful in your ears. I apologize. So I've set this up again. I'm going to repeat. You write your DEQ or your DEQ. Here it is. You immediately use the SECT model to solve it. This is the starting amount. It will be handed to you. This needs to be found using point number 2 of growth. So solving this for k, I'll divide both sides by 0.00372. I would natural log that. I would be left with 8k because the natural log will undo the e. And I divide by 8. Remember I said it's the natural log of the growth factor divided by the time? That's exactly what I have here. But go through the steps for now. And now in Calc 2, we'll cut this process in half. But for now, we're going to leave it as it is. So this is going to give me my K. It will be negative. I know that because the concentration's going down. Negative 0.066228. Negative 0.066228. I would suggest you store that in K since there's more questions. Well, you don't have to if you want to. It doesn't matter to me. So let's wrap this up. So the doctor says that you're going to have serious body damage. You're going to grow an 11th finger, or your leg's going to, I don't know what's going to happen. Your hair's going to turn green, but serious body damage if the concentration was ever this high. So that, let's think about what that means. Based on my equation, let's go write it. The concentration at any time t, now I'm writing it more with function notation just because I like to, is equal to the amount at the start, handed it to me, e to the k, and I have it stored, or if you want to write it in there, you could replace that as well. That's your decision to make. The question is, do I have the potential of having some serious brain damage? Was the concentration ever as high as 0.015? You have to use a little common sense here. When would the concentration have been at its highest? And go back and read the question up at the top. When would the concentration have been at the highest? It would have been when you inhaled some poisonous fumes. When did you do that in reference to this problem? Because we need to plug in a t. I can't plug in a 20 because that'll send me 20 hours from when I want to go 20 hours ago. So we need to have our t send us back and use a negative 20. So my concentration 20 hours ago, or my C, is going to be 0.00372 e to the stored k, and I'm going to send this back 20 hours to when I first was stupid enough to inhale those fumes. And if that's over 0.015, I need to worry. If it's close, I might have a headache for a while. If it's well under, no worries. It'd be like, it's looking like I've got 0.013989 on my calculator. So let's answer the question. Serious body damage if it was ever this high. Well, I was 0.013. So and that would have been at its highest. That was at first inhale 20 hours before I went to the doctor. So the answer to this would be no, but close, right? Close. I wonder what the body damage would have been. You grow a third nipple, right? Just kidding. I'm getting punchy. I've been doing this a long time. All right. So homework. you need to just go take the Schoology quiz. It's 10 questions right off these notes, so have them out because I ask you for some specific numbers. You should get 10 out of 10 if you watched it authentically. And then on Monday in class, we'll just dig in, do a few together, talk a little bit about some Newton's Law of Cooling, and work on a worksheet. Ciao for now. Peace out, Girl Scout. Where's my pause button?